This section is entitled Inferences about two means, where you have independent samples. The first thing I'd like to talk about will be independent samples versus dependent samples. In my opinion, I think it's best to talk about dependent first. Dependent. We have two samples, sample 1, sample 2. And they're dependent if you can pair up the data, pair up the samples in a meaningful way. Has to be in a meaningful way. You can always pair up data. 7, 8, 11, 13, and 15 if they're the same size. Another sample, 11, 22, 43, 18, and 29. So the top numbers is sample 1 and the bottom numbers are sample 2. And you can pair them up. You can pair up 13 and 29 and 18 and 25. 18 and 15, excuse me. I didn't even say what the samples are. There has to be some meaning behind pairing them up. There has to be some logical reason why these two numbers get to be paired up. The classic example would be, say, you're doing a study on some kind of a diet pill. In sample 1 and sample 2, you have 5 people. The same 5 people in both samples. And you're going to record their weights. The 5 people are called number 1, number 2, number 3, number 4, number 5. And sample 1 will be the before weights of these 5 individuals. And of course, sample 2 will be the weights after they complete the diet. Maybe the first person weighed 173 pounds, person 2, 202, person 3, 179, 213, and 112 pounds. Now you have the after. Person 1, after 3 months of being on the diet, she weighs 161 pounds. Person 2, she weighs 179. Person 3, he weighs 184 pounds. Person 4, she went down to 129 pounds. Person number 5, 107. Now, there's an obvious pairing. You can pair up those two. You wouldn't really pair up the before weight for person 1 with the after weight of person 3. That just makes no sense. But if you can pair them up in a meaningful way, then we say that these two samples are dependent. A necessary condition, a must for two samples to be dependent, they have to have the same sample size. But that's not enough. If they don't have the same sample size, they can't possibly be dependent. If they have the same sample sizes, they might be dependent. You have to think, can you pair them up in a logical way? In a way that, yeah, I understand this. Person number 1 went from 173 pounds to 161 pounds. I understand that. The diet worked for this person. Person number 2 went from 202 pounds to 179 pounds. Seemed like the diet was really good for this person. Person number 3, on the other hand, they went up a few pounds. Person number 4 was amazing. Went down almost 100 pounds. 84 pounds they went down. Diet was fabulous for person number 4. Greatest diet ever, this person would say. But to pair up 173, the before weight of person 1, and the after weight of person 3, that makes no sense. You know, somebody before weighed 173, and now somebody after weighed 184. That's meaningless to us because they're not paired correctly. Okay, so just because you can pair them up any old way, that doesn't mean they're dependent. You have to be able to pair them up in a reasonable way, a way that has complete, it's sensible. 173, 161. Person lost 12 pounds. 202 to 179. Person lost 23 pounds, etc. Now, independent is when you can't pair them up in a sensible way. You can't pair up the two samples. Suppose in this first example, the diet was diet pills. Okay, just diet pills. Okay, person number 1 went from 173 pounds to 161 pounds. Well, let's just change this. Suppose we still have actually 10 people. 10 people. Okay, we have 10 people. And the first person, in sample 1, we rarely do give diet pills to them. And after 3 months of this experiment, that is, after 3 months they started taking their pills, person 1 is 173 pounds, person 2, 119, person 3 is 374, person 4 is 205, and person number 5 in sample 1 is 178 pounds. Okay, those are 5 individual people who were in this study who took diet pills. And there are their weights after 3 months of taking these pills. The second sample also had 5 people, not the same 5 people in sample 1. And these 5 people took placebos. They took sugar pills. They didn't take any diet pills. And their weights, the weight of the person number 1 in sample 2 is 214, and the second person in sample 2 is 111. Their weight is 111, etc. 149, 281, and 114. So one sample of 5, they took diet pills, and the other sample took placebos. And if you think about it, there's no way of matching these up. There's absolutely no reason why you should think that 173 should be matched up with 214. There's as much of a reason for the person in group 1 who weighed 173 pounds to be grouped up or paired up with the person in the other sample that weighed 111. I mean, there's no reason why 173 should be with 214. Why not 111? Why not 149? They're just random people. Okay, in the first case, number 1 in sample 1 and number 1 in sample 2 were the same person. They were the same person. Of course you pair or an individual person with themselves. It was logically sound. But in the second scenario, it's independent samples. You cannot pair them up in a meaningful way. I mean, again, you can pair them up. I'm not going to say no. You can pair up person 1 in sample 1 with person 3 in sample 2, and person 4 in sample 1 with person 2 in sample 2, and you can pair up the number 5s in both sample 1 and sample 2. You know, you can pair them up because they have the sample size is the same, but it has no meaning. That's what it's about. To be dependent, you have to be able to pair up in a way that's logically sound. Why would you take person number 1, let's talk about the diet and the placebo experiment. And you have, in each of those groups, you have a person number 1. Why would you compare the weights of person 1? It has absolutely nothing to do. Now, okay, there's no meaningful reason to look. Let's see what the 2 people who we call number 1, let's look at their weights in 3 months. Now, maybe they started off with the same weight, but that was not given. Okay. Now, as always, in each section we talk about the requirements. What are the requirements to use problems in this section? And the first one is that, well, let me number it this way. The first one is, remember, the title of the section is Inferences about 2 means with independent samples. So the first requirement is the 2 samples are independent. Independent. That's condition 1, requirement number 1. Requirement number 2 is that sigma 1 and sigma 2 are unknown. Now, what is this subscript 1 and subscript 2? Well, we have 2 samples. And like always, if you have a sample, you can find the standard deviation. Okay, well, we have 2 samples, sample 1, sample 2. Sigma 1 is the standard deviation of the population of the first sample, the people who took their diet pills, versus sigma 2, which is the standard deviation of the people who took the placebos, the sugar pills. And the third one, like always, N1 has to be bigger than 30, and N2 has to be bigger than 30. Either those 2 conditions are met, or both samples are normally distributed. N1 is the sample size of the first sample, and N2 is the sample size of the second sample. The next thing we always talk about is the test statistic. Talk about the formula for this TS. And in this case, the t-test is x bar, x1 bar minus x2 bar, the sample data, the sample average of x1 minus the sample average of x2, minus mu1 minus mu2. And this all gets divided by the standard deviation of the sample for 1 over n1 plus the standard deviation squared of S2 over n2, the square root of that. And like always, when it comes to the t-table or t-distribution, we have to talk about the df, the degree of freedom. And most books, not all, most books, they use the smaller of n1 minus 1 and n2 minus 1. Now what does that mean? For example, if N1 was 70, so N1 minus 1 would be 69. And if N2 was 74 minus 1, that's 73. We would use the smaller of those two, which is 69 in this case. We use the smaller of the two. And like always, the next thing we talk about, so let me just get rid of this example. The next thing we talk about is the confidence interval. The confidence interval estimate. Okay, the confidence interval estimate of, remember, the title of this section was The Inferences About Two Means. So we want to talk about the difference, mu1 minus mu2. Are they different or not? And this is for independent samples. And the formula is like it always is. It's x1 minus x2, x bar 1 minus x2 bar, minus the error. And that's less than mu1 minus mu2, which is less than the difference of the sample averages plus e. And let's see where I'm going to sneak this in. Maybe I have room right here where e is equal to t alpha over 2 times basically what's right here. S1 squared over N1 plus S sub 2 squared over N2. So we need to know x1 bar and x2 bar, and then we need to calculate E, meaning we need to know T alpha over 2, and we need to multiply it by that square root part. To find the confidence interval, it was always something minus E is less than what you want, which is less than something plus E. In this case, the something is x1 bar minus x2 bar. Okay, so let's consider a couple of problems. The first one is a study was conducted to assess the effects that occur when children are exposed to cocaine before birth. That is, what happens to kids when they grow up and before they were born, their parents were using cocaine. So we do some kind of a test. We see how well or how long it takes them to play with building blocks, to make a tower. Okay, how long does it take kids who are say 4 years old now? And so we'll have two samples. Both samples of children will be 4-year-olds, and one sample, the parents did not use cocaine while they were pregnant with their kid. And the other sample, the parents did use the mother, I should say. The mother did use cocaine while she was pregnant with the baby. Okay, so we have two samples. Sample 1. Mother used cocaine while she was pregnant with the child. And when the kid was 4 years old, they were tested. Okay, 190 children were tested. And it turns out that the average, so X1, the average of these 190 children is 7.3. And the standard deviation of this sample, which is S sub 1, little s1, this is a 3.0. Maybe I should write sample 1, not S1, because we're using S1 for standard deviation of the first sample. And of course now sample number 2, the mother did not use cocaine before, while she was pregnant with the child. And it turns out that there were 186 children. 186 children who are now 4 years old and whose mother did not use cocaine while she was pregnant with the kid. She could have used it before, she could have used it afterwards, but not while she was pregnant with the child. And the average length of time was 8.2. With the standard deviation of 3. Okay, one moment, please. Okay. All right. So now we want to use a 0.05 significant level to test the claim that cocaine exposure or cocaine use is associated with lower scores, lower times. Okay. So now, okay. So that's our claim. Cocaine use is associated with lower times. Now, the cocaine use came from sample 1. Now, the HO is always equality. HO is that the two means are different. Now, what's the claim saying? Cocaine with an E. Cocaine use is associated with lower times. So what they want to say is that the sample that uses cocaine, sample 1, is lower than sample 2. And since that does not have the equal sign, we call that H1. Okay, let me put it up here to save space. Remember, if it said less than or equal to, if it said that cocaine use is associated with not lower, not higher times, that means less than or equal to. If the claim was less than or equal to, then the H1 would have been that mu1 is bigger than mu2. Don't use H1 when it has the equal. Okay, we went over that in the past. Okay, so we have the claim listed, it's in the box. We have the null hypothesis stated, and mu1 equals mu2, and we have the alternative or alternate hypothesis tested. So now, of course, we go and we find the test statistic. We know that t is equal to x1 bar, 7.3, minus x2 bar, which is 8.2, divided by the square root of, now we do s1 squared, which is 3. Well, s1 is squared. s1 is 3, you square it, you get 9, and you divide it by n1. The sample size was 190 children, so it's 190, plus s2 squared. s2 is also 3.0. You square it, you get 9. Then you divide it by n. For sample number 2, there were a sample of 186 children. And you crank this through, and you get some kind of a number. The number is negative 2.908. Okay, and we hold on to that number. That's the test statistic. That's the cutoff. Now, since we want less than, it's a one-tailed test, and they told us to use a 0.05 significant level. Now, the DF is the smaller of the n minus 1s. 190, 186. If you take away 1 from those numbers, the smallest number you'll get is 185. Okay. If you did 190 minus 1, you get 189. Like it said, you use the smaller one. So the DF is 185. Now some tables don't have 185 or 189. Then you go to 200. And if you look this up, you're going to come to the conclusion that t is equal to negative 1.653. And I made one mistake. I'm so sorry. This negative 2.98, that's the test statistic. That's not the cutoff. Sorry about that. That's not the cutoff. The cutoff is what you get from the t table. Now let's get rid of the DF because it's right by my graph. So from the table, we got negative 1.653. Okay. And 2.908 is to the left of it. This is a number line. Here's 0. Eventually you'll have negative 1.653, and then further to the left, you'll have negative 2.908. Like I've always said, what's in here is the acceptance region, except you can't say accept, but we'll think it. And accept HO. That is fail to reject it. And in here, we reject HO. Okay, let me get rid of a lot of this writing on the top, and then we'll write up our conclusion. Notice I very carefully left the claim, because we need to decide if we accept the claim or not. Now, the first thing I'll say is we reject the HO, because only if you're in here, all the way up to t equal negative 1.653, do we accept the HO. But we're at negative 2.908, so we reject HO. We reject HO. Now, it turned out that H1 and the claim are the same. There's sufficient evidence to support the claim. That the means are different. There is sufficient evidence to support this claim. To support the claim that cocaine use during pregnancy yields lower times. Lower times for the offsprings when they are 4-year-old. When they're 4-year-old. So there's clear evidence that parents should not use, moms should not use cocaine while they're pregnant. Let's try another one. This time we'll use, or we'll calculate an interval, the confidence interval. Now, this one actually interested me. A study was done regarding birth weights and IQ tests years later. If you had more weight, if you were very low weight at birth, the study suggested that you'll have a lower IQ test when you're 8 years old. Right. So, sample number one. Here's just the information on sample number one. 258 8-year-olds with low birth weights. Were given an IQ test. And their average score was 95.5, and the standard deviation for that sample number one, that's why I put a little 1 there, is 16. Sample number two were people who were kids who are now 8-year-olds who did not have low birth weights when they were born. Okay, so you have 220 8-year-olds, say, with normal birth weights. And they, since it's sample 2, the average will have subscript 2, and the sample standard deviation also will have a subscript of 2. Okay, your parents have 2 children. They give them different names. We have 2 averages. We have to give them different names. Average 1, average 2. 2 standard deviations. Standard deviation 1, standard deviation 2. Don't get caught up with that. 2 samples, sample 1, sample 2. Take a wild guess what we would call everything if there was a third sample. We call it X bar sub 3, S sub 3. Standard deviation, sample 3. And the information here is their average score was 104.9 and the standard deviation of 14.1. So the scores, these scores really do look a bit higher than the 95.5. Now, we want to construct. Let me try to sneak it in here. We want to construct a 95% confidence interval estimate of the difference between the mean IQ scores. Between the difference of the mean IQ scores. So between mu1 and mu2. Okay. So we need to calculate, say, E. Remember, it's going to be mu1 minus mu2 is in between x1 bar minus x2 bar. We have that. We have the x1 bar and the x2 bar minus E, which we have to find. The right side, x1 minus x2 bars. We have that, plus E. So the whole job is to really find E. Doing x1 minus x2, that's not a big deal. That's not a big deal at all. Finding E, that's a big part of this problem, if not all of it. 90% of this problem is finding E. Remember, E is T sub alpha over 2 times the square root of S1 squared over N1 plus S2 squared over N2. Now, alpha is 100% minus the 95%, which is 5%, better known as 0.05. So alpha over 2, if you divide the left side by 2, you have to divide all the sides by 2. You get 0.025. And when you look up the 0.025 with their DF of, degree of freedom of, well, the N1, sample 1, N1 is 258, and sample 2 is 220. 220 is smaller. So when you take away 1 from 220, you'll get smaller than when you take away 1 from 258. So the degree of freedom is 220 minus 1, which is 219. And when you look that up under the one tail, well, actually, that's not true. It's a two tail. It's a two tail. So I guess one of the things we should have talked about, and I kind of blew that, is what's HO and what's H1. Always H1, since we're talking about the means, they're equal. Now the problem said construct a 95% confident interval estimate between, well, okay, I take that back. We don't need this. We don't need this. Sorry about that. We don't need this. Okay, so when we look this up, what we're going to get for a two-tailed test when we have 0.025 in each tail, and we have the degree of freedom of 219, we are going to conclude that T sub alpha over 2 is going to be 1.972. Do these long enough, you learn, well, maybe, okay, it's 1.972. Okay. You can look up two-tail, 0.025, the degree of freedom. You're going to have, 200, maybe 300. Let's see where my table has. Yeah, 200 to 300. And above 300, which doesn't matter, is 100. You're going to pick the number by 200. You look under the two-tail heading at the top under 0.025. You go down to 200, and you're going to see 1.972. Okay, that's why I picked that number. Okay, let's get some more space back. Put back the 1, 14.1. Okay, so now we have the cutoffs. Now we have the T alpha over 2. We now have this number right here. So the rest is just plugging in. The rest is just really plugging in their information, the values, using the formula. This number is 1.972 times the square root. S1, 16. Please, please don't forget to square it. Divided by N1. Sample 1, 258. Plus S sub 2, which is 14.1, square it, divide by that sample size, which is 220. Okay, calculate that square root part, multiply it by 1.972, and the value that you get is 2.715. 2.715. Okay, so need to erase a bit. Try to be slick and put it right here in the middle. That way we still have the X bars in front of us. X1 bar, X2 bar. Well, I need to know what X1 minus X2 is. Now, just for the record, if you do X2 minus X1, instead, it equals to the top as long as you put a minus sign in front of it. This is worth mentioning again. I know most of you use calculators, and to be honest, that's too bad. I don't think you should. But if somebody asks you what 7 minus 10 is, instead of doing 7 minus 10, which you might think is hard, you can do 10 minus 7. You can read it backwards and get 3. But then you better change the sign. If you want to know what 10 minus 22 is, you can do 22 minus 10. And if that means you have to actually write it down and do it, fine. You get 12, but negative 12. And why am I saying that? Because X1 is smaller than X2. Instead of doing 95.5 minus 104.9, you can do it backwards. And what you are going to get if you do it backwards is 9.4. But you do it backwards, it's negative. That's X1 minus X2. That's X1 minus X2. And that's a big portion of the formula. The formula is X1 minus X2, negative 9.4, minus E, which, remember, E was right over here, and it equaled 2.715. So we take away E. Actually, this one should be plus 9.4. We take away E, 2.715. This is less than mu1 minus mu2. And this is less than 9.4 plus the 2.715. Right, and you do the arithmetic, and that will be it. On the right side, you get 12.115. On the left side, you get very close to like 6.7, I bet. 2.715, 85, 6, 6.685. And that is what mu1 minus mu2 is in between. It's in between 6.7 and 12.1. That's the confidence interval. And that finishes this section. Good luck with it.